Alright, let's make sure.
But then I think it will take some time to
Should be a regular mouse here.
There we go. Okay, there we go. Right on time. We'll see what happens.
Yeah. He's come to our place a couple times, but I think he was.
All right, we're 1 minute to go. We're
Let's wait a couple of minutes because we don't have UCs. Bill is here. Who else are we missing?
We're missing David.
And Shane? Missing all our locals.
So you're going to tell us how we're going to go fast, is that right?
In a way. Yeah. Part of it, anyway. So,
One goal to collect the tomography.
of course, I'm only going to look at a very small part of the processing.
So then what, if you're going to try?
Wordt goed.
All right.
It's ours, not yours. So it should be okay.
Okay, sure.
So it's a
Thank you very
copy,
much.
but you'll see that at the bottom. It says output.
Thank you very much.
So I think what, we're just missing David
He
Agar,
works
is
for
that
FBI.
right?
Late David. Yes. Late David, yes. So now is he working with Manfred?
30 minutes.
You're gonna follow after.
So we're just missing David and Sean, I think, yeah?
Okay.
Anyway, they were late yesterday too. Say again? No, the Max will work on us. RGA.
Do I have trained?
Don't sit down.
Very well done.
All right, let's get going.
Yeah, let's get going. So you're, my understanding is you are not actually a biological cryo.
This is true. I'm not even in cryo EM. I have done work on EM at least, but
You're not biological.
but yeah. But I'll introduce myself and
okay.
our group a little bit. So I'll yeah.
Doesn't trust you.
So yes, good morning. I'll be, so the title of my talk was real-time processing for high-throughput cryo, and it took a little bit of a liberty here, and I kind of removed the cryo bit, and I'll just talk about tomography in a broader sense. So to introduce myself, because I'm very new to this community, I'm a mathematician. I have a PhD in number theory from a previous life, but now I've been in tomography for about 10 years. In a various range of modalities, lab, X-ray, CT, synchrotrons, and STEM, but I haven't done any work on cryo-EM so far. I'm the lead developer of a software package called the Astro Tomography Toolbox, which is, for instance, the GPU-accelerated part of Inspect 3D from Thermo Fisher nowadays. And I work in the computational imaging group at CWI, which is the National Research Institute for Mathematics and Computer Science in Amsterdam, in the Netherlands. So our group is led by Joost Batenburg, and we are about 18 people now with a very broad background, so from mathematics, computer science, physics, engineering, and also branching out into the medical and life science slightly recently. And we work across on a broad range of applications across various modalities and try to really bridge the theoretical and experimental research communities in the fields of tomography. And since last year, we actually have our own, we're actually an experimental group now because we have our own lab X-ray CT system, which we call the FlexRay Lab, which is really intended to be a flexible system, so it's not focused on any one specific sample, but it's really focused to be very flexible and be able to emulate and prototype lots of different scanning trajectories, modalities, and different types of setups, so we can really work on the methodological parts of the tomography pipeline. And as an introduction, I'd like to highlight a couple of the EM projects we've done in the past. This is all in material science. So this is a bimodal dark field stem combined with energy dispersive spectroscopy. So here it's using, let's see, there was some kind of pointer. Yes, thank you. So using elemental information at a low resolution combined with the HDF image at a relatively high resolution, and combining them to get the best of both worlds and get a high resolution chemical specificity. Another one is in the HDF stem world to correct for nonlinearity in the modeling. So a typical assumption is that the acquired sinograms are linear in the density of the material and the thickness, but of course there are lots of physical things getting in the way, and so one of the projects we worked on is trying to model this nonlinearity and correcting for it, which then greatly helps in the post-processing. So here there's all kinds of coupling artifacts, but if you correct for this nonlinearity, then it becomes suddenly much easier to segment the gold and silver in this nanoparticle. So in this talk, I'm going to talk about real-time tomography, and so of course there's lots of different potential interpretations for what real-time can mean. So it could fast acquisition, dynamic experiments, fast reconstruction, visualization, processing, analysis, and even all the way to adapting your imaging parameters on the fly based on this fast processing analysis. Now I'll go over a range of projects in our group that fit somewhere in this set of things that could fall under real-time tomography in some sense. So to start, and make sure we're all on the same page when it comes to terminology and context, I will give a brief couple of minutes. I will talk about tomographic reconstruction in general. I'm assuming you've all seen this before, but I'll go through it relatively quickly. So what I call tomographic reconstruction is the part where you go from a sinogram to a tomogram, to a volume. And so there's the well-known radon transform, which takes some sample and it projects it onto the detector, and you get images, and the tomography problem is then, so this is a sinogram, and it's going back from a sinogram to your 2D or 3D volume. And the typical algorithm used for this is the filtered or weighted back projection, so called filtered back projection in some communities and weighted back projection in some others. And this is based on the continuous analytical inversion formula, which gives an exact reconstruction, and then it's discretized to form an approximate reconstruction. And so I'm going relatively quickly because I'm assuming you know. And of course, you run into all kinds of problems if you have you're not in the full continuous regime. So you have a very limited number of tilts, then your image quality deteriorates, and you get these typical streaking artifacts. In the electron microscopy world, you of course have this missing wedge where you get all kinds of, all your circles become ellipses or are stretched out anyway. And the bottom line is basically that filtered back projection works very well if you have a large number of projection angles, a relatively constant angular sampling pattern, and your noise level is not too high. And in the tomography world, there's been lots of work on trying to improve reconstruction quality even if you're not in this regime. And that basically starts from not from the analytical model, but modeling your tomography problem as a set of linear equations. So you assume that every measurement you have is some line going through your sample, and that gives you an equation of the intensities of the pixels lying on the line to your actual measurement. And it gives you a linear system, and you can solve this linear system using a variety of methods. typically iterative methods because your systems are huge, billions of equations, billions of unknowns. And so these iterative methods, they basically start from something and they try to gradually improve your reconstruction based on your data. And there are lots of reasons why you want to use them. So you are much more flexible in your scanning geometry. You can incorporate more complex physics models. You can add constraints such as non-negativity of your attenuation coefficients. You can incorporate statistics to better account for noisy data. And you can include lots of prior knowledge, and especially in the material science field, there's lots of prior knowledge in the sense you know what kind of materials there are, you kind of roughly know the shapes you're looking for. And the kind of results you get from that is if you have a filtered back projection, noisy reconstruction, where it's only barely possible to see the outline of your sample. If you do an iterative reconstruction, it becomes suddenly much easier to see your sample. Another popular thing in the past decade, say, is exploiting some kind of sparsity. So if you know that your image has some nice structure, and so this is of course a very nicely structured image. So this is a so-called total variation regularized thing, where you assume your image has relatively straight edges and constant areas. Other popular things are wavelet-based reconstructions, where you assume your object has some structure which can be represented naturally in wavelets, which may or may not be the case in your samples. So this is one of the popular things in the past decade, say, exploiting this kind of prior knowledge and sparsity in some domains. A thing we've done relatively much on ourselves about 10 years ago is a field called discrete tomography. So that's especially relevant in if you know what kind of materials there are going to be in your sample. And so this is a rat femur, so bone, with some soft tissue which is completely invisible at these X-ray energies. But also in material science, you often know exactly that there's going to be gold and silver in my sample. And using this prior knowledge, this is a very strong prior knowledge, and then you can really high quality reconstruction from extremely limited data sets by adding this very strong prior knowledge. So these are some of the examples we've done. So these are more nanoscale things. So the core shell nanoparticles. I think this was some kind of nano. No, I'm not sure what the sample was actually. This is some more brick-like lattice structure. So these are all from the material science world. And this has gone all the way down to work also down to atomic resolution using discrete tomography to really reconstruct atomic lattices for nanoparticles. And these algebraic methods, they work well for more complicated geometrical setups, for limited data situations where you can add this prior knowledge to compensate for this. And the big problem if you have a lot of time and computing resources, because these iterative algorithms, they are orders of magnitude more slow than the standard weighted back projection reconstruction. And if you add these prior knowledge, then you add another level of complexity. Now,
So
for
the discrete tomography, how many levels? Some of your examples look like they were just binary. But
Yes.
are there applications where you would use 2 levels or 3 levels or some such thing?
Yes, so we have, for up to about 4 levels, we've gotten reasonable results. You can go a little bit higher, but it becomes...
After that, you might as well do continuous.
Right,
Yeah.
it becomes that much trickier to do the
And
segmentation.
if you do more than 1 level, do you
Mhm.
have to know what the relative ratio of the second level is to the first? Or, yeah.
It helps. We've developed a couple of algorithms in our group to work on this. So the first one that really assume you know exactly what indeed the ratio is between the densities. Then there's another set of algorithms which does not assume this anymore, and then it tries to basically iteratively estimate these values at the same time.
Got it.
So it alternately tries to fit the gray values and the sample. Yeah. So as I said, this requires a lot of time and computing resources. Over a long time, the feeling in the community as well, we can just add more computers. GPUs the GPUs arrived, GPUs keep getting faster, we keep getting more and more cores. But looking back, not only were computers getting more powerful, also detectors were growing. So where when we started, well, a 1K by 1K image was very high resolution. Now 4K detectors are quite normal. So this is from the X-ray world. I've been here. I heard similar numbers like 4K images here as well. I think. I'm not sure
Or
how
larger.
Hmm?
Or larger.
Or larger, exactly. So even though computers are growing fast, it turns out that detectors and data sizes are growing even faster. So we can wait for faster computers, but it will just get more. We'll just fall behind more. So these reconstruction methods are. So if you use the grid rec thing, it's a little bit faster than n to the 4, but iterative algorithm n to the 4 and to the 5. If you keep in mind that you need to increase the number of iterations. And so even going to parallel computing or even massively parallel with GPUs or clusters, it's hard to keep up with anything more complex than FVP. And we do want to keep up with this.
Sorry, just one last thing on the discretized. If it's quite simple number of levels,
Mm-hmm.
do Monte Carlo methods work? You're just
I
trying
don't
to
know.
flip a coin at each pixel and saying, are you on or off, right?
Yeah, so-
and there may be, sort of other kinds of algorithms that are very different than these, reproject error kind of calculation things.
Yes, although you do.
I mean, in the
still
end, you
have
still
to
have to project,
fit
yeah,
the
because
data.
that's the data,
Yeah.
right? But you don't have to do the forward projection. You only
right,
do the
because you're only flipping a pixel
Sorry,
at
you
a
only
time.
do the
Yeah.
forward projection. You don't do the back projection.
Right.
In a model like that.
Yeah,
right?
so that's the more coordinate descent-based methods, I guess. So where you flip pixels
Yeah.
or try to optimize pixels. Yes, this is done. We haven't tried this with discretes in particular because there, as you say, you do have the coin flip. So
Yeah.
it's relatively easy to optimize each individual
Yeah.
pixel. So no, we do go relatively in a similar direction by, this algorithm DART I mentioned, that basically tries to optimize the boundary of the sample with the assumption that
right.
you assume the inside and outside are relatively okay, but you want to optimize the boundary. And so this is also a relatively
Right.
small set, so
Yeah.
they're also, you get a performance boost by not looking at the whole sample. Yeah.
You also
Yeah.
assume that you already have aligned images.
Yes.
Yeah.
So this, so I'm really looking at only a very small part of the whole processing pipeline because basically I'm not from the Cryo world, so I don't know and can't work on the other sides. We do work with lots of EM data, so I mean there are the alignment problems. I don't know, I can't compare if they're just as big or bigger or smaller, but alignment is definitely one of the main issues in material science EM as well, of course.
And the complexity of the algorithms for aligning are similar in terms of.
Yes. So it's from what I hear, it's the techniques used are fairly similar. Although I think there's still less. So this Protomo package that I heard about that does, or maybe EM Clarity also does alignment, if I understood yesterday correctly.
Protomo, yes, the EM Clarity has a bit different principles. It's just,
Yeah.
but yeah.
Yeah. So there's. Yeah. So yeah, I don't have a full picture of both the Cryo EM and the material science EM world, so it's hard to give an in-depth comparison between the strengths and weaknesses. But it sounds from at least the distance as if the techniques used are very similar on both sides. Okay. As I was saying, we do want to be able to keep up with data acquisition with the reconstruction steps. And so the typical tomography pipeline, sort of, you've seen similar things before, so acquisition, some pre-processing, at least what we call pre-processing because it's before the reconstruction, segmentation, analysis, visualization, and then you start to actually process your data. And the direction we want to move is where there's a feedback loop going from the analysis or visualization of your experiment back to the acquisition. And this is, so the main use case for this are either in situ experiments, so if there's something changing in your sample, dynamic experiments, in situ experiments, or for instance, you want to do some pressure testing of a sample and you want to do some kind of process until you see something change in the image, then change the parameters, change the pressure, increase the pressure, and then continue scanning. And another use case for this is, so this would be an algorithm deciding when to process, or a human deciding, looking at the images, when to proceed with your data acquisition, or when to change your algorithm parameters. So what we mean by real time in this context is that your reconstruction has to happen during the scan and at the same time as the data acquisition. So you're really able to get images on your screen at the microscope or at the lab while the experiment is running.
So does that mean that you can start your reconstruction right after you get first projection?
Yes, exactly. And I'll show examples of this later. But that's really indeed the idea, to speed up reconstruction to this point. And we have some things running. I'll show that in a bit.
How long is one scan?
So that varies a lot, of course. So in synchrotron, it's sub-second. Lab CT order of half a minute. To the EM case, where it's of course significantly longer for a tilt series.
Sorry.
Yeah.
And how many scans do you usually have? Like how many images you have in a site?
This can go up to thousands for lab or synchrotron data sets. Okay, so in the rest of the talk, I will go over a couple of projects we're actually working on at the moment that are related to these things. And so the first one is from the EM world. So this is continuous tilt tomography. So this is the group from Jülich who did this in 2015 with a single electron detector, and they did 1000 hertz imaging of a nanotube. And so now I hope the movie is going to work, but it's excellent. So so this is a tilt series. It's very noisy. You can see the carbon nanotube lying on the grid here, and it's so this real scan happened in 3.5 seconds, and this is slowed down for the movie. And our group did some of the reconstructions for this. So this was not in real time because it was a discrete tomography situation. And so this is the reconstruction we got out of this using an algorithm based on Dart with also this automatic gray value estimation in it. And how that looks is, I'll show some cross sections. So this is comparing the search, so a standard iterative reconstruction on the right to the discrete tomography reconstruction on the left, where it's clear that the structure of the nanotube is really much more well defined. You can see parts of the support structure here as well.
Okay, so that answers the question if the stage can be faster. This is a Titan stage.
Yeah.
Okay, so this was real-time acquisition, but not real-time reconstruction at all. So this took quite some time.
So I mean, any comments about, because this is relatively high magnification, right?
Mhm.
It's a no.
So what's the dimension here?
Because I thought the nanotubes were really pretty wide.
I'm afraid I can't answer dimension questions on this sample.
Okay.
Well, what do you mean if you go back? It looks like a lacy.
Carbon, yeah.
Pretty small field of view there.
Yeah.
Is it?
Well, that was because of the camera, right? I mean, that
They
was a
had a
very
tiny
small,
camera.
yeah. To get that
to
readout.
get high
right?
readouts.
Yeah.
Yeah. Okay, so this was basically a small aside because it's very relevant for.
And do you know what the
it's,
angular tilt range was?
Yes. So this went from minus 70 degrees to plus 30 and a bit, I think.
What's the missing wedge error?
Yes, there is a missing wedge. So it's go up, up to plus 30. So it's 100 degrees tilt range, and so in the search reconstruction you can really clearly see the missing
Oh, and
wedge.
yeah, right.
And the discrete tomography approach corrects for that quite significantly.
Does the discrete tomography approach work on really low dose images?
So this, at least from my point of view, this image was relatively low dose. It's not really in the cryo world, I know. in principle, yes, that should not be a big problem. The bigger problem in the life sciences is probably that you're not able to use this discrete assumption quite as strongly, because cells are just much more messy than material science samples.
It's not clear how far off. I mean, so often we look at things, and at the end of the day, you pick a contour threshold, and then look at your structure at that threshold.
Right.
Right. And so, it's with 2 or 3 levels, that may be all one really needs as a decent beginning for biological
Right.
samples.
It might work that the rest of the differences are kind of absorbed into the noise anyway,
Yeah,
and
yeah,
it's
exactly.
Yeah.
But I noticed in the Dart reconstruction that that a lot of the lacy film isn't very continuous. I mean, there
Right.
are big holes in the there, like
Yes.
here, right? Whereas presumably that's a continuous thing in real life,
Probably,
right?
yes.
Yeah. So, I mean, is that something that having chosen another level would have fixed, or is that this is a single level? I take it, right? This is binarized.
Yeah, so this is 3 levels vacuum.
Oh, 3 levels.
Well,
It
I
is
mean,
3 levels, okay.
So one of them is vacuum,
Yeah,
vacuum,
right.
and then
Yeah.
nanotube and support, I think.
I see.
So
Sorry, how did you align this series?
that was done by not by us, but so. Sorry. Now, given that it's that this is 3,500 images, so the relative change between them is very small. So presumably basic cross-correlation-like approaches would
And this
do
is
quite well.
Compared to ours, very high signal to noise
Right.
for an individual
With sharp
slice.
edges and yeah.
So this is not a real time, right? Reconstruction.
The reconstruction here is very much not real time. No. No. So, but I'll move to the real time parts now. So as I said, so there's the classic back projection. It's very fast, but it has its limitations where your data quality is limited. And then there are iterative algorithms which model it in some algebraic way, which are slow but much more accurate. And one of the approaches we're working on is to adapt the classic filter to weighted back projection by changing the filters in some way. And I see here the Mac has more trouble with the formulas, but that's you can probably get the gist of the idea. Basically, what we do is we take the standard filter back projection and just modify the filter in some way. And one of the first things we tried here in 2012 is trying to optimize the filter by trying to approximate the SERT algorithm. So you try to you really take your filter as part of an optimization problem, and you try to fit it to get the same reconstruction that SERT does. And so a typical Ramlag filter in real space looks like this. So,
Ripples.
Yep. And if you adjust it to a SERT, it becomes more angular dependent, and it becomes a bit stranger. So part of the thing you see in it is the size of the reconstruction window, which is a square here. So you see that reflected. But it could also adapt to a missing wedge, for instance, if you give SERT the projection geometry of your real experimental setup. And what
But
happens?
this would be SERT without sort of a positivity or without any of the nonlinear aspects,
Right. This,
or
yes,
region of constraint
exactly.
or anything, right? This
So,
is just okay.
Yeah, this assumes that that it's a linear algorithm,
Right.
so you can use various tricks to
Right.
estimate it quickly. And so what happens here, if you have a phantom that models some kind of foam, with FBP you get a very noisy and streaky image. SERT gets a more structured, also somewhat more smooth image. And the FBP SERT reconstruction here now gives pretty much identical results to SERT, but also with just a single filtered back projection step, so at the speed of FBP.
So how do you optimize the filter? What's the cost?
When you're asking questions, do you mind speaking up a bit? Then the workshop people, the external people.
So the question was, how do you optimize the filter?
Yeah, how do you optimize it?
So in this case, you assume that basically so FBP has the filter of FBP is the effect of modeling a point spread function in space, and you try to map the output of a SERT algorithm to this, and then you have an optimization problem where you basically need to find a few you need to sample the results of SERT for some impulse. So you get the impulse response of the SERT algorithm, and then you plug it into the filter. So this was not the fastest. This was kind of the initial experiment. And later, we started to assume translational invariance of the FPP algorithm to kind of approximate some things and avoid having to compute the full impulse response of the SERT algorithm.
But that you only have to do once per sample geometry.
Exactly.
Right?
Yes.
So for a given data collection geometry, plus minus whatever, some increment,
Yes.
then you know, however long you spend
Exactly.
doing that, you can then just invert that into a matrix, right?
Exactly.
Yeah.
And so for another sample, if you have a very noisy sample in this case, instead of a limited number of angles, you see that also the FPP SERT reconstruction matches the SERT reconstruction very well. So you get part of the benefits of iterative reconstruction, but without the computational cost, except for this pre-computation. Okay, so another approach for computing filters is not optimizing it just to the geometry, but actually optimizing to the data. So the thing is that the filtered back projection algorithm is a bilinear algorithm, so it's linear in both the data and the filter. So also, if you have the data, you can see it as an optimization problem to get the best filter to get the best matching reconstruction to your data. And so that means that what you get is you get an adaptive filter that adapts itself to the conditions of the scan. So if you have a very, very noisy image, that it will automatically smooth the data more. If you have a very well-defined image, you'll get a relatively sharp filter. And so, so some of the reconstructions here with various electron or photon counts, so from 2 to the 6 to 2 to the 10 per pixel, and you can see that the filter approximates or gets very good trade-offs between smoothing and sharpness for various noise levels automatically. So so this is a way of adapting your filter to the data and getting the right low-pass behavior without actually having to manually optimize this. And this also works for missing wedge, for instance. So if you have if you compute an angle-dependent filter tailored to the data, it will automatically detect and adjust for the missing wedge, greatly reducing the streaks and elongations around the corners. But of course, it is still an FPP algorithm, so it is limited in what it can do here. So these are some of the basic filtered back projection methods we've worked on. Another one for the prior knowledge. So total variation regularized reconstruction is very expensive to do in the full volume. However, it is possible to do it, to limit it to a region of interest. So this is, the idea here is that it's more or less a local approach. So the impact of things around the region of interest are limited in magnitude. So if you if you apply your TV term only on the region of interest and do something relatively simple on the outside of the object to approximate the contributions of that, it is possible to limit computation efforts and only so do a low resolution or simple reconstruction for the outside of the object, and then do your region of interest with the TV regularized approach to give relatively good results at relatively limited computation.
So how do you determine the residuals though? If you're just in the against the projection, if you just have this small area?
Yeah, so you do need some kind of low resolution reconstruction of the outside, and so filtered back projection is good enough for that. And there will be errors around the borders, but they will be very, very limited. And especially in the center, you'll get something that's very close to a full TV reconstruction.
Yeah, I guess it depends on, what fraction of your area you actually care about.
Yes, right. Although this is a relatively small inset already, so it's it worked better than we expected.
And because we'll probably have, in a lot of biology things, you'll have, even out of the 4K by 4K image, maybe you only have a 2K by 2K region of interest, right? It's still an awfully big
that's
region,
still
right?
going to cost a lot of performance. Yes. No, so this is say going down to region of interest of maybe 100 square pixels to get to keep it reasonable reconstruction times.
What does TV stand for?
It stands for total variation, and it's a term that basically depends on the smoothness of your sample. So large constant areas have zero total variation, and sharp edges also don't impact it too much. So it will try to promote large constant areas and relatively sharp edges between them. Not necessarily, but at some point, yes. So a typical approach here would be in filter back projection initially, and then later focus your computation efforts on the region you care about.
Is that like around the square region? Do you have artifact on the boundary between like the region of interest and
Yes. So you do need to make sure that your region of interest is has some margin of error.
How does this behave as a function of noise? If the image is very noisy, does it still reconstruct the piecewise constant images?
Repeat the question.
Yeah. So the question is, how does noise influence this? Will it still get piecewise constant areas? And the answer is that this is a complicated situation. So these algorithms, they typically have a so-called regularization parameter, which you kind of have to tune to balance between the data fit and the regularizer. And so this is something that comes. There are lots of heuristic methods for trying to estimate this, but in the end, everybody really just still does it manually and tries to manually adjust and see what the best trade-off is for the questions you want to answer in your sample. Because it's very hard to automate this. There are lots and lots of heuristic approaches that work very well in some specific questions and not at all in others. Okay, then the next topic is going into the learning direction. So we have a couple of projects, like the rest of the world, I suppose, that try to do something with learning for tomography. So this one is one of the first approaches from 2014. And here, this is a single layer network, so this is not deep learning, but regular learning in some way. And this is combining filter back projection with different filters. So the network basically has weights that correspond to the filter of the filter back projection method, and then combine these in a nonlinear way. So you get some filters that try to, or at least seem to try to fit edges, some of them try to do regions and low frequency components, and in the end there's a nonlinear combination of them to get something better than what filter back projection can do, because there's a nonlinear component in here. And so this of course does need training data, so you need to have high quality data from somewhere, and then you can use this to train a network to improve the performance of the filter back projection method, or at least a couple of filter back projection methods. And learn this. And this got some quite decent results from quite some samples. So here a typical approach would be to use a lambda CT for the low resolution data and a synchrotron for the high resolution data, or sometimes do expensive iterative reconstructions on a couple of slices of your sample to get high quality reconstruction, and then train a network on that to also get relatively high quality data for the rest of the slices. Of course, this does depend on that you need the features of interest in your slices, but this is a problem that the whole learning community has to deal with.
So how many neurons do you have on this kind of typical network?
Right, so the modeling here is that every output pixel has its own network, and so in this case it would have four hidden nodes. So this is
He's asking, is a convolution neural network?
no, this is just a single layer perceptron, and so it turns out that if you model every individual output pixel as a single layer perceptron, maybe two layer perceptron.
Your training set and your test that need to be kind of aligned.
Yes. But on the good side, modeling it this way does mean that every individual pixel in your data set gives a training example, so you have lots of training data already from a few slices. So in going into the deep learning direction, so this is now using, again, work of Dan Pelman, which is much more recent. using a more complicated network to do post-processing on the filtered back projection reconstructions. And so this is on the left, it's a normal FBP reconstruction. On the right, it's an FBP reconstruction with the NNFBP method from the last slide. And in the middle is a full deep learning multi-scale network to do the post-processing. And so this is learning on a large set of synthetic data that resembles some kind of foam. And that foam on the top and more continuous sample with some weird geometric inclusions at the bottom. And here the network really quite accurately reproduces the ground truth of these samples. So this is starting from a low quality. So this method starts from a low quality FBP reconstruction and cleans it up using the information learned from the phantom data set. And this is now also giving quite good results for real data sets.
And sorry, are the phantom data sets that are used for training, are they no noise data sets, or are they those, also including synthetic noise?
These include synthetic noise. Yeah. No, it's we try to approximate the real data as closely as possible to get a good, at least a relatively good hope that it will work.
What are the labels?
Sorry?
What are the labels?
No. So in this case, it's this is not labeled. This is just a continuous.
How did you train?
So just using the mean squared error between the ground truth and
it's a regression.
It's a regression.
Classification.
Yeah, exactly. Okay.
So once it's trained, is it fast?
Yes.
Yes.
It's not. Yeah, it's in the same order of magnitude as the filter back projection reconstruction, and it parallelizes very well as well. Okay, and to finish, I'd like to show a piece of software we have developed, and especially Jan Willem Buurlaag, who is a PhD student in our group, to do real-time quasi-3D reconstruction and visualization. So this, what you see here, it's a movie of a real-time reconstruction of a 3D volume, and what happens here is you have a user interface that lets you take slices and tilt slices, move slices, and see the reconstruction on that slice in real time. And the main idea behind it is that many properties of your sample can already be seen in a slice. And using FBP, so because FBP, the formula for FBP, basically every pixel gets computed independently. You can compute a slice FBP reconstruction pretty quickly, and not just ortho slices, but any slices in any orientation. And because you only have to reconstruct a couple of these 2D slices, that means you can really go to real-time reconstructions, or for quasi 3D reconstructions. And so to give you an impression of these times, so if you have a 1K cubed volume and you want to do a couple of 1K squared slices, you get update frequencies with, if you use 4 GPUs, of about 40 milliseconds. So you have a 25 Hertz updating reconstruction, which basically means that if you drag and move these slices, you get pretty much real-time, or at least perceptually real-time reconstructions of those slices. And this is something we have implemented at a synchrotron. So this is a movie at, it might make a lot of noise when I start it, but I don't know this laptop. It's fine, okay. So this is at the synchrotron at the Tomcat beamline at the Paul Scherrer Institute. And here, what you see is a sample of I think it's actually just normal shaving foam. And it starts spinning and as you see it spins pretty quickly, so there's multiple full tilts per second. And here you can see live the reconstruction, and the resolution of the movie is not that great, but you can really see the edges of the foam. You can rotate around it, you can zoom in. Sorry?
When you turn like that, it's going to change the shape.
Yes, yes. So of course, with the experiment design, you have to model the speed of rotation to how much rotational forces the sample can take. But so the nice thing is, while it's scanning, basically the reconstruction is updating in real time to the conditions of the scan, and updating in real time. So if you look carefully, you can see the bubbles growing and changing and rotating in this case. Okay, that was my last slide. Thank you very much.
Any other questions or comments?
At first, Astra script, we have been using that for testing for a while, and it's pretty useful for just code testing and reconstruction.
Good to hear.
And I have two questions. One is, do you think so? What essentially is the sparse assumption of the sample, and do you think it holds true for this biological sample at all? Since all this thing we'll look at is hydrogen stuff, and I don't know what degree the sparse hypothesis may still hold true, and what can you do without it, and what kind of hypothesis we can use for our sample.
Yeah. So the question for that is what kind of domain you would be sparse in, and so one thing that has, I think, been tried for life science samples is the wavelet domain, which. But it's really a very sample-specific question, and I'm afraid I don't have enough experience with cells and life science imaging.
We just need to find a domain that our sample is sparse in. Kind of find it yet.
Things like wavelets or shearlets or curvelets, those have a standard chance.
Some domain that. The second question is, you were talking about the growing speed, but what about memory consumption? One problem when we use Astra, the only major problem we have is just it crashes when we have feeding big things, and it's out of memory all the time. And
so this so parts of Astra, and then especially the directly integrated iterative algorithms, they have memory constraints, but the filter back projection, the forward projection, and the back projection steps, they do not have memory constraints.
The fancy stuff crashes all the time.
Yeah. So so this is a documentation problem, because we also have an implementation of CERT that does only the forward and back projections.
We have been using that and having all kind of funny things going on, but I think it's something like this to use.
So when I ask what model do you use, so you do, because when I was doing reconstruction like SART, and we always had a wall model, like wall volume in 3D, so we can shoot the rays, and we can do extend very easily all the fancy things without like any additional cost. And then we solved this memory issue by just slicing. So we always had only partial slicing, because you can also divide it by that, just keeping the thing. So I mean, we never really had a memory issues even with iterative methods. So I don't know.
Right.
Do you have a similar model, or do you have the really wall module?
No, it's also divided into slabs. And,
so it should not really.
No, it's we just have so our standard CERT implementation basically does assume you have the full volume in memory, but there's an alternative CERT implementation in Astra that does that swaps in and out on demand.
Do you have experience in collecting randomly distributed increments instead of fixed increments, so this will get rid or help with aliasing issues?
You mean so tilting less regularly, or
non-uniform increments?
no? And I mean, it should. I mean, there on the implementation side, it just works, but I have no experience with how that would affect your reconstruction quality.
You will have the sticking artifacts that will be less dense, but other than that, it's okay.
If you have periodicity in space in some way, then if you're just sampling fixed increments, then you're not going to get rid of, you're going to alias. So how do you know if you're
I really want to shake hands. We almost do everything Astra, if it's not the question. Anyway.
Thanks very much. I can bring in.
Okay. So my talk is toward integrated pipeline for quality data processing. It's Nguyen Chen from Bielefeld Medicine. So it's an intense talk, so let's start. So we all know there are many steps in the data processing pipeline of Cryo-ET. And nowadays people do different steps in different software, like someone would reconstruct tomography in iMod and pre-package in EMAN and do the supply imaging in real life. So today I'm telling you an integrated approach that essentially everything in EMAN. Sure. There is obvious benefit of this integration, and we'll see later. So in the first step, Q-series alignment, we have developed a landmark-based iterative approach for this Q-series alignment. So the idea is essentially we have a very coarse alignment, then just build a tomogram from it. And it will be a very low quality one, but we can pick some 3D high contrast landmark from the low quality tomogram, and then we project it back to Q-series and use this projection of coordinate to refine the alignment parameter, and then we have slightly better alignment, and we make tomogram again, and repeat the process. And it turned out it can improve iteratively. So here, it chooses in this case blue shows, and after first iteration you see it's crappy, and after fourth iteration it looks like something. And the tomogram slide field looks nice too. This is an equalizer or expressing a drag pump. So this takes about 5 to 10 minutes per tomogram, the whole process from the time you input the Q-series to the point you get the reconstruction out. And it has been pretty robust on our data set we tested, and it's fully automated. You just push a button and it just reconstructs all tomogram in the folder.
Did you do any features to effectively have some auto masking around the landmarks so that you're
Yes.
doing a good job of
There are many
segmenting?
heuristics in the system that makes this thing work.
And does it work for non-bead-like things?
That's why I'm having this one. So the reason we call this landmark-based, not fiducial-based, is because it works without fiducial.
Well, but those are all bead-like things. Those are all round.
So one thing I showed like this is, as a whole, the landmark as a whole is not bead-like. Even each individual of them is, it all still aligned based on this cluster of beads. And you see something like this. This is not bead-like, and this is not really bead. If you filter everything to say 500 angstrom, everything's bead-like, right? But right. Anyway, my point is, it works without fiducials. Like in this fiducialist case, I just pick those ice continuation as landmarks. In some cases, pick just ribosome and do the alignment, and you have a pretty nice tomogram from it. And I will show you that the tomogram just need to be good enough for visualization, the particle. You don't really have to be very, very good. So keep going. One thing we have to mention is, although we had a version that used extra, but we end up using our direct Fourier inversion for tomogram reconstruction. Since we are doing everything in EMAN, we actually have a pretty good scheme for just reconstructing stuff. There are two limitations. The major limitation is when you're reconstructing something big, there's a memory consumption issue and it's slow. So the solution is, first we do everything by tile. So we truncate Q-series into small pieces and reconstruct them and put them together with overlapping. And second, we only generate bin 2 or bin 4 output tomogram. So what you get is just the bin filter tomogram that you can visualize and pick particle. So of course you need full sub-tomogram for averaging, and we'll talk about later. Good. Okay, now we have a tomogram in like 10 minutes. Then we want to annotate them. I've been talking about the automated convolution neural net-based annotation for a while, so I won't spend too much time on it. So now we have integrated this into our pipeline, so you don't have to import and export, and we have better interface and bookkeeping for the networks you train and the segmentation you have, and you can extract particles from the annotation. Then you have something like this. So we modify the interface a bit, so now you can look at multiple features in one tomogram. Like in this case, it's a flagella from a trypanosome. We pick some microtubule duplet from the flagella and some ribosome from the cell body. And the next question is, we only have bin tomogram. How do you generate unbin particle for averaging? Answer is easy, because we make our align the Q-series ourselves in the transform. We just map the particle coordinate back to the Q-series and extract the sub-Q-series to make sub-tomogram. And before doing that, we can just have pressure. So because we are reconstructing each sub-volume from those sub-Q-series, we can actually do a per particle per tilt CTF correction. That is, if you do a stripwise CTF correction, you get the defocus out here. That's the average defocus of the time. But once we determine the defocus of the tomogram with a global optimization based on tiles, we calculate the defocus of each particle based on the position in ice, and we correct the CTF per particle per tilt, and with the CTF correct particles, we build them into a CTF corrected 3D volume. Next, now we have 3D particles, initial model. It's not as important nowadays, but I think it's a very interesting thing to me because once we have a very robust approach for that, we can actually just look at random things we're interested in the cell and build an initial model out of it, even without knowing what they are, and just refine the structure. Sometimes we have sub-nanometer resolution before we know what it is at all. But that's true. In this case, it's stochastic gradient descent. It's super powerful for neural network training, and it works. You have 30 particles, and you can get a pretty nice initial model out of it, be it a tubular structure like this, or ribosome, or in this case, those pumps across both membranes.
But I mean, those aren't those kinds of resolutions, right? I mean, the microtubule doublets are certainly not sub-nanometer.
No, this is initial model.
Yeah.
You can refine it to sub-nanometer afterward, the calculator.
So you create an initial model from unbinned data?
During the creation, it is binned. After we unbin it and for the further refinement. You can make it unbinned too, it's just slower.
No, I was just asking because.
Next, refinement. We do this in a two-step approach. The first step is very similar to what we've always been doing. We define the orientation of each subvolume and refine the map. After we have a somewhat higher resolution map, we refine the orientation of each subfield. We call it per particle per tilt refinement. Because we make particle from the subfield, we can usually just from the orientation determined earlier, just slightly refine it in both the orientation and the translation. And in the ribosome case, after the subtone refinement, we get to 13 angstrom. That's an Ampere data set that's from Python. And after subtone refinement, we get a resolution that's similar to the Python resolution. And after the subfield, we get 8.5, and that's similar to the EM clarity resolution. And we thought it won't work for a cell, but it does, not as significantly. So for this pump with 1300 particles, we get to 19 after subtomogram refinement and get to 14 after the subtilt refinement. And at this resolution, you can fit in the model and see the channel inside. Finally, so we also have tools for heterogeneity analysis, and including the classical PCA and focus classification. And I think the most interesting thing of doing classification in situ is you can look at different classes and how they interact with the environment. Like in this case, you can release the mass, can see how your protein interacts in this case with the cell wall, and you can map them back to the tomogram and see how different particles distribute on the membrane. Okay, finally, we have a few project management utilities. One thing we've been talking about is once you have the hydrogen tomogram, how do you know which are good, which are bad? So we have this interface that you can preview that each line is a tomogram. And when I get a big data set, I just start by loss. That is the alignment error. And
sorry, can I just go back for
Sure.
quick to the per particle per tilt alignment?
Yes.
Right. I guess the question is that's a lot of parameters.
Yes.
Right. For what amounts to being a relatively small, noisy volume.
Yes, it's also very constrained because we have the subtomogram alignment already, so we only let it shift a little bit in that region.
That only means your searching range is small. That
Yes.
means the number of the parameters they are going to
No.
refine
It is
small.
still right.
Right.
I mean, so you don't have any kind of continuity constraint? You're not saying, well, everybody in the neighborhood has the
So-
same
Has
tilt on that
similar
picture?
behaviors.
So you can, I try to include that a little bit, and it seems to just give me a very similar result. And I think one thing, it's a similar thing I am clearly talk about, because your particle, when you have a dense tomogram, your particle overlap, and that essentially give you some constraint in that sense that kind of
But this
softens
is at a per
everything.
particle. I mean, EM clarity is doing it at the level of the kind of entire reconstructed volume, realigning the tilt. It's not doing it at a per particle level. And so the
There are
signal.
patches, yeah.
What's that?
There are bigger patches.
Yeah,
like
I mean, it's
this.
way bigger
So
patch.
bigger
right?
bigger
And so,
patch.
yeah, it's like
Bigger patch. In this case, the subtilt is twice the size of the subtomogram. we padded quite a bit before we do this.
Yeah, but you're only aligning based on your particle, right? And so it doesn't, that's just for avoiding edge effects, right? Is that what I
Yeah,
mean?
partly, yes.
And do you fix the alpha angle at the measured angle?
Right.
And so,
So,
and does
our-
angle vary much, or is it really all translation of each tilt?
Mostly translation, but the angles vary slightly. So, in my experience, it doesn't the like before and after all the angle and translation doesn't vary that much, especially when your tomogram is reconstructed well. But I think that just boost the resolution, just give you a tiny difference that increases your final resolution.
And what kind of angular changes you get? And you say if you fix the alpha, then you're not allowing for any of the
No,
changes
I'm
coming
saying
from doming.
I fix alpha by it. The alpha can be adjusted based on the matching between the subtilt and
Okay. And what kind of ranges of, shifts and angles do you?
Usually within the range of the tilt between your in your T series, like you have 3-degree tilt, you shouldn't expect your tilt go all the way to here, right? It's between the last and next tilt.
Well, I think the question is, what's your searching range?
It's not a brute force in a range search. It's a little bit more heuristic than that, so it's hard to tell. It's like the search range. It's closer to a Gaussian distribution with a sigma of your tilt angle.
And so, what do you actually use for subtomogram averaging, like a CC, cross correlation?
FRC, of course.
FSC.
Yes.
Particle to
Particle
reference.
to reference FSC.
Okay.
Yes. Yeah, we always use FRC for 2D, FSC to 3D, and with the missing match composition.
I have one more question. So, how do you deal, because you said that this is still Fourier reconstruction, right, per particle. So how do you deal with an interior problem in Fourier case?
So, depends. I think there are two situations. If your cell is very thick and your particle is very deeply buried in the cell, then essentially you're not expecting to get half Nyquist. Then we don't. We just extract particle from our bin-2 tomogram and do the subtotal averaging, and we don't get half Nyquist, so we don't care that we don't really need a full tomogram.
Yeah, no, that's
Right.
that's not what I'm talking about. I'm talking about the fact that there are severe artifacts from interior problem. They are very easily to be avoided in a real space reconstruction. They are very tricky to be avoided in Fourier reconstruction. That's why
You mean in the reconstruction
in the
of the
reconstruction?
tomogram?
Yes, exactly. If I reconstruct the particle, how do you assure there are not artifacts from interior problem in your subtomograms?
When you say reconstructing a particle or reconstructing a tomogram?
Reconstructing a particle, because you said that for bin2 you...
Yeah, so yes, my point is, when you have very thick cell and you want to look at things that in the cell, and you really worry about this thickness, the interior problem, you don't. You reconstruct tomogram and you do the traditional way, you extract particle from it and do the averaging. You only have bin2 tomogram, and the highest resolution you can achieve is just bin2, but in that case you're not expecting to get to half Nyquist anyway, so it doesn't matter.
Even for thin samples like HIV, you still have the interior problem.
So for purified sample or even for cell like this, it turned out it works fine. I think we have been playing with the padding and the interpolation kernel a little bit, and I think we get to a point that we are kind of more or less happy about it. There are a few tricks in that. For example, when we do the interpolation for the reconstruction, we use a Gaussian kernel with varied radius for different radii. But when you get to the high radii, you use a bigger kernel, so you have more information included because the information is more sparse here. So my point is, we play with a few data sets, and we kind of heuristically find the set of parameters that seem to work.
And can you change these parameters as a user?
If you really want, you can. It can be a bit messy, but
my point is more like, do you still have some assurance that it's more or less mathematically correct? Because based on my experience, the fact that you don't see the artifacts doesn't necessarily mean they are not in there, because we have very noisy volumes, right? So do you have some mathematical assurance to say that you can still do it per particle?
Yeah, I think the main mathematical assurance is the projection and Fourier slice theorem. So essentially what you
Yes, but
which
this
have had-
slice theorem actually requires that wall object is in your field of view. Which is not true even for the
it
bigger
requires you
reconstruction.
have a soft edge that it's not saying all volume, everything's in a volume, but your edge is soft enough that the boundary effect doesn't kick in. So we did many things to prevent that. First, when you do the reconstruction, at high tilt, actually mask it along the y-axis to make sure the information in the tilt series is the same for each tilt. So at 0 degree mass like this, at high tilt we mass like this. So essentially all the information is in the volume, and we do a soft edge decay and extra padding. So we did many things to make sure this is not at least very essential problem, and it seemed to work for many cases we have.
So you should try to wrap it up.
Yep. Yes, I know. So anyway, so when I get a 100 tomogram, I just reconstruct the home folder and sort everything by loss. And look at the bad ones; they're usually bad. Something funny happens in the usage. And same thing comes for the refinement. When you have multiple structure from a same project, you can go through them and see how good you do in each one of them. And other than future direction, we want to integrate this as much as possible into the data collection pipeline. And of course, we want to solve high resolution for smaller proteins. And the more interesting thing I've been doing is now we can identify on those things inside a cell. As I said, if you see something interesting, some interesting pattern, you just make an initial model, average them, get high resolution. And from the structuring, you can actually go back and tell what it is. Of course, with some mass spec data. And we want to solve heterogeneity, continuous heterogeneity in situ, that you don't see open state and closed state, but you see a transition from open to closed state. And that's it.
Didn't you say it was 5 to 10 minutes for the alignment and reconstruction?
Yes.
What kind of machine is that on?
My 6-year-old 12-core workstation.
How do you decide which tomograms to keep and which ones to delete? What are your criteria?
So we use our loss function is essentially the landmark projection versus the landmark position in tilt. It's somewhat similar to the fiducial error, but it's not always fiducial. So it's similar, but not mathematically straightforward. But in practice, my experience is usually the higher number are worse. And when you have a set of tomogram, you usually have a curve like good ones and bad ones. So it's usually pretty easy to distinguish in my experience.
Yeah, I want to drag us back to this issue of the reprojection, the tomogram alignment.
Can you speak up a bit, David?
Yeah, basically, I think what David was referring to, you've got to do something to this thing you picked as a landmark before you reproject it to say, well, it really looks more like looks more like this, and that's what I'm going to reproject. Because if you just reproject what you got right there,
then you won't get anything, right?
Yeah.
So yes, we start from it being 8, and at very low resolution, we just use the highest peak, the center of it, the only like the 1 pixel information projected back.
Okay. So
and at higher resolution, we use center of mass, because we are closer to the ground truth already, then you can adjust it a little bit. And we do it the progress way. In the first iteration, we only keep like 70% of the best tilt and try to make the rest 30% mass spectrum. And in the last iteration, we keep like 95%.
Okay, so it's got lots of little
there are little things in there to make it actually work.
And do you do that by, sort of like a refinement, or by taking those points and actually calculating what the geometry
we do
would be
global
as
refinement.
if they were
We do
fiducial?
a global refinement.
But you just treat them as fiducials, or do you do it as an image-based
We do the
refinement?
image-based.
It sounds like you're incorporating initially the assumption that whatever's most dense there is just a sphere,
And everything else is zero.
I think the
Yeah.
assumption is the dense thing has a constant center of mass along the surface. The center of mass in each tilt doesn't change the location of it. It's kind of true.
Yeah, I guess.
Wow, it looks
Yeah,
like
if it's
that is
round.
everything.
It's not always
Yeah,
always
right.
the highest.
This is like
Here's the center of mass.
bunch of
If you
keys
have
on
more
the
highs,
on
it
the
can
ring,
melt
and
in
then
the process.
it's connected. It's connected.
Well,
How many
Yeah,
batteries?
that's good.
I mean, in projection, you know.
Did it again. Exactly.
It looks just like the connections between the
Is it all?
Yeah, take any kind of.
Hey Dave, so off
Sorry,
this
what
stuff,
you
you have
say?
to go a little with an outline for the loss.
Sure.
Yes.
Yeah.
Put
Yeah,
something
over
on
the
paper
copy
and
break.
perhaps,
Yeah, yeah,
and
yeah.
then perhaps together we can just edit it.
Sure.
Yeah. And we can go to their screen whenever they go. I guess they want to go on.
The center of mass and the mat.
So if you have a pair, if your object
All right.
Object really isn't something
I have another one.
experimentally true. But there's gonna be
Is the
enough
data
out there
on
that
time?
is. That's the thing.
Yeah.
That's how
No,
you
no,
get
I
it.
understand.
Yeah.
Oh, one second.
So that's how you
All right.
wait.
Yeah.
Thanks, Manas. If you could take us through the last book of the session.
See, algorithm learning, I don't think we realized this when we put together the
How could you have missed it?
No, I'm sure it was deliberate. It was totally deliberate.
Well, my name is Manas Raj, and I'm at the Center for Computational Mathematics at Flatiron Institute. Firstly, I'd like to thank the organizers for the invitation and opportunity to present this work. And this is joint work with Alex Barnett and Leslie Greengard at Flatiron Institute, and we've been trying to extend work done by Nico in template matching. So very quickly, what's the science fiction goal that we are after? Hopefully, in a year or so, the fiction part will go away from it, and it will only be science. It's that given these tomogram slices in 2D, can we, and a collection of proteins that we wish to identify, can we label the translation locations and the rotations in which they're present in each of these slices simultaneously for a multiple batch of proteins? I'm not going to go that far today. Today I'm just going to talk about where we have a single instance or a collection of instances of the same protein in different orientations in simulated data for the time being, and try and understand what the threshold is for protein size and signal to noise ratio in idealized environments, as that would set the threshold for more complicated real data sets. So what has been done in this regard is one of the standard approaches in this direction is to do template matching, where you compute 2D projections of your molecule and then just compute cross correlations and identify peaks of this cross correlations. This has been implemented very successfully when the proteins are large, around greater than 300, 400 kilodaltons in size, particularly for proteasomes and ribosomes. And the reason those things work well is because you can get away with sampling a very coarse set of orientations. As you keep on reducing the size of the proteins and typical signal to noise ratios that you see in cryo images, it gets really hard to detect smaller and smaller proteins. And Nico in his work had mentioned that there is some threshold of 150 to 300 kilodaltons of protein size that can be detected in these environments at the signal to noise ratios there are. So our work in this direction has been, for the timing, has been to first accelerate the approaches that Nico had developed while getting the same set of results in terms of accuracy and retrieving the locations and the orientations, and later on also try and see if some of these methods can be extended to reduce the threshold of the size of proteins that can be detected if the images are clean, or by using multiple slices obtained in the same cryo setup. Right. All of you all know this very well, but again, I'm a mathematician, so I have to lay down notation of what I'm going to do. The model is the following. You have your epiferritin molecule. That's the forward model. You're going to orient it in some direction through some rotation matrix R, and compute the projection of that along the z direction. I know that's not all of the physics, and it's a little more complicated than that. There's the CTF in the picture, right, and this is really just the phase information. But at the end of the day, mathematically, this is an equivalent formulation even after all of those transformations, because we assume that we're in the weak scattering regime, and you can just look at the phase as a linear function instead of the exponential in that setup. Another thing you don't know is where it's located in the tomogram, so it can be located at some arbitrary location x0 in the tomogram, and you have a lot of noise. And for the time being, I'm going to make another assumption that the noise is Gaussian and IID. It's not a fair assumption, but there are ways to get around that as well. And in the end, you're given some sort of an image that looks like that. And your goal is to identify the best possible rotation R and the best location x0 at which this molecule is present, or say with some reliability that the molecule is not present at all in this environment. And if you write down the maximum likelihood estimate, that's a favorite estimate in this setup, you're trying to, you say that the likelihood of finding, given this image R, the likelihood that the molecule is at x0 and R is given by this product of Gaussians. And your goal, and you say that the best rotation and translation is the one that minimizes the log likelihood. All of this is just fancy ways of saying that if you look at the cross correlation, that is the thing that you're trying to maximize to minimize the log likelihood in the environment that you're assuming that the noise is Gaussian. If you do not assume that the noise is Gaussian, if you have some idea about what the power spectrum of the noise is, you can bake that information in as a cross correlation, as a correlation matrix in this model, and you would get some other parameters where you're trying to minimize the image with the template with some matrix sitting over there. Right. And another assumption which we have made is, and it's not necessary to even if you look at simulated data, is that when you're trying to optimize over rotation and translation, you have this term which is the energy of the projection. And that is not a constant when you look at it as a function of the rotation. We haven't yet understood what the effect of including this term and minimizing the whole thing is as a function of the rotation and translation. But for the time being, we're going to assume that that's constant and just look at the cross correlation. So what does this mean in terms of CPU time when you think about a typical calculation? So suppose you have n pixels in your image. The typical images that I've been looking at have been 1080 squared. Nico is looking at images of similar sizes. If you're looking at the epiferritin molecule, to be sampling at twice Nyquist and making sure everything is safe and sound in terms of Fourier space, since we're just testing limits with respect to SNR in the setup, you end up with a template which is of size roughly 360 squared. And the way you lock into the right molecule or right protein here is by sampling the number of rotations at a large number of points. So the larger the protein is, the smaller samples you would need in rotation space to make sure that you've locked onto the right rotation. But the smaller you make the protein, the effective number of rotations that you would need to keep on sampling at will increase. And unfortunately, because of the curse of dimensionality here, if you want to improve your resolution by a factor of 2 in orientation space, you would have to increase the number of rotations by a factor of 8 because it's a 3-dimensional space. Right. And the two tasks that we need to do in order to compute all of the cross correlations is firstly compute all of the templates, and that can be obtained very rapidly using the Fourier slice theorem. So you just take the 3D Fourier transform of the scattered potential, and then you can use some sort of cubic interpolation to compute it on slices. And that would take, for each pixel you're just gathering information from 27 neighboring pixels approximately. So the amount of work you do is the number of pixels in your template times the number of rotations that you end up with. And then once you have this template, you want to compute the cross correlation, which is just a convolution between the template and the image, and that can be computed very rapidly using fast Fourier transforms. There's a log n factor missing over there, but n is small, so log n is practically constant for all of our cases. And if you now add up all of these numbers together, unfortunately you'll see that the amount of time that you need to compute all of the cross correlations in this setup is roughly 100 CPU hours. So what we propose in this setup is do some sort of frequency marching. Filter both the image in terms of translation resolution and rotation resolution to find neighborhoods in which you get decent logs. You might not know exactly where the molecule is or at what rotation there is, and then use a finer grid in the neighborhood of the 5-dimensional space associated with the 2 dimensions of translation and 3 dimensions of rotation to go up to the higher grid resolution. So we tested this, and again, our goal is to just understand what the thresholds are with respect to molecule size and signal to noise in the idealized setup and get some speed up for the same algorithm. So here I have 9 copies of epiferritin at some random orientations.
And you have no dummy things in there that are decoys?
Not yet.
Okay.
That's the next set of tests we're going to do. We're just going to have a pool of proteins and then add in Gaussian noise and see how the algorithm performs in this setup. That's our next step. And we look at 4 signal to noise ratios, where the signal to noise is I have defined as the norm of the template divided by the norm of the noise, or the standard deviation of these things. And if you look closely in up to a signal to noise of 1/20, you can actually somewhat see the images. For 1/20, you need to really look at it very carefully. But when the signal to noise is 1/10 or 1/5, it's very clear what the image looks like. So what we did is we tried 7 different strategies of coarsening and then refining onto a finer grid to see what our success is in terms of locking onto the right translation and the right rotation. And we declared an experiment to be a success if we are within 2 pixels of the right translation and within 3 degrees of the right rotation, because the finest grid of rotations we were looking at was roughly a 3-degree grid. So these are our 7 strategies. S1 represents the fastest, and it's in increasing order of time taken to compute these things. S1 is when we are filtering our spatial variables by a factor of 2 and filtering our rotational variables by a factor of 4 and doing nothing else. It's just seeing how many times do we lock on. And we did 30 experiments for each of the signal to noise ratios. S7 is our finest strategy, which is use the original bin 1 grid that we had in terms of translation, but use a rotation grid which was 2 times coarser than the grid that Nico had used. The reason we stopped here is because otherwise the CPU time is much larger, and what we believe is if you want to compare how frequency matching would work for this as a starting point and then going to the finer resolution, you can just compare how the coarser strategy works as compared to this finer strategy, and all the picture would do is it moves higher towards a much lower signal to noise ratio. So if I did plot Nico strategy and did some frequency matching there would be a similar fall off in the S7 curve, but Nico strategy would work for even a lower signal to noise ratio. And again, as I said, this is an idealized environment. We want to reproduce these curves and see what these curves look like when you have a crowded protein environment in this setup.
Is there a way to predict whether any algorithm would work, like a minimum variance bound or something, that you can theoretically really predict whether the estimator will find anything at all? Is that something you looked at?
Yes, so that we have some derivation as to what are the relevant quantities that show up in terms of theoretically predicting what would work and what would not. And what's relevant is the norm of the Fourier content of the molecule at a certain radial frequency taken, its inner product with the norm of the noise at that frequency, and how does that compare with the variance of that noise at that radial frequency. And that's a good estimator. That's a good model for saying whether something is going to work or not. And that is work in progress.
Great.
In the setup. First, we just wanted to accelerate and see what kinds of accelerations we get while being able to reproduce what they had done in the paper. So this is just that. So we also wanted to see if there was any effect of just filtering our translation directions, and so we did a very coarse search even at the right translation. So we would always lock onto the right translation. And then strategies 3 to 6 are our frequency matching approach. So we start with either results from S1 or S2 and look at the top 250 candidates in that list and say, okay, near these top 250 candidates, we're going to zoom into a grid of S7 where we take a finer grid of 32 points or 64 points in the neighborhood of each 5-dimensional point, and then do the fine search again. But to do those searches, you do not want to do Fourier transform because you're computing like 64 inner products. So you stack them up as matrices and send it to BLAS. Standard packages will do matrix multiplications, and that's what gives you the speed. So we looked at looking at top 250 candidates and top 1,000 candidates that you get from strategies 1 and 2, and then doing our fine search. And what we observe is when you're working at a signal to noise of 1/10, if you start off with the core strategy and then do the fine search, you get 100% recovery. When you're at a signal to noise of 1/20 with Gaussian noise, if you're doing just the core strategies, you're doing worse than if you did the core strategy and then zoomed into the finer strategies, and you just miss out on 1 out of the 30 cases in terms of locking at the right translation and the right rotation. And at a signal to noise of 1/40, the picture is pretty grim. None of the strategies do a good job, and you need the complete fine search.
So, but I mean, if you had looked at the top 10,000
Oh, there was nothing there. I checked that. So it really capped off over here. And after at a certain point, the cost of looking at a certain range ends up filling up all of the space. So there's no CPU time gain.
Right.
Exactly. So we also wanted to maintain a CPU time gain between each of these strategies to then say, if you're not getting a speed up, why do it in the first place? You can just at that point work with the finest resolution.
So is there understanding of why that is?
Of why there was why this is the right signal to noise ratio.
Why it didn't work well at that, why the correct.
So this is something
wasn't in the top, and presumably even if you started with S2 instead of S1 and did all your marching from S2.
Right. So that's S5 and S6 is starting at S2 and then doing a frequency march, and S3 and S4 is starting at S1. So that didn't really make much of a difference. So because, and I think again the estimate really lies in looking at now different molecules and looking at the quantity that I just mentioned as to what the frequency, once you filter things out, it has a certain frequency content that you're trying to sample, and if you don't sample that grid sufficiently, you can just end up picking the zeros and missing the peaks completely. And it's a tricky balance between these things. So when you don't look finely enough, you essentially just miss the peak completely, and Nico had done studies in this regard as well to show what the width is of typical peaks as a function of rotation when you're locked into the right translation.
I mean, is there a way of renormalizing the power spectra of the search object and then also use that same renormalization for your image? So you take areas that are kind of weak at, say, the middle resolutions, you boost those up, and then you also do a comparable boost for the whole image.
Right.
Does that now give you better discrimination at the lower resolution searches or with your...
we haven't tried that, but we should try that. So it would be an interesting strategy to try to see if that makes a difference when we're doing our courses searches.
You're going to boost the noise power in those frequencies too, right? So the ratio between the two should stay the same. If I'm not understanding.
Well, but you have a lot of incoherent stuff, right?
Okay.
That, the thought was maybe all that just kind of randomizes and cancels out, much more, and so you get the root 2 or whatever benefit, by doing that, to put more power where you can afford to look.
I have a question about the SNR definition that you have. So you have the norm of the object, but that object is compact.
Yes.
And you have the norm of the noise, but the noise is not compact.
Yes.
So it depends on the size of your whole image.
Right, so the image size was 1080 over here. So I renormalized the object to be standard, to be variance 1, and then I add in a noise which is of variance 1 over SNR square.
Okay.
Yes.
That's a problem, because if you change your size,
right,
then that ratio change.
Because the zeros are included when you calculate the variance of your...
Right, because your object is compact. It doesn't fill the whole thing.
No. So the object is normalized to have variance 1 as viewed as a whole image, not as viewed as the compact
but
object.
it is compact, because everything else is 0.
But, sorry, I meant the standard deviation. If you divide by the same factor of square root of n.
Yes. But in standard deviation, your whole size is included.
If you take your image and you pad it by zeros, does your standard deviation change?
No, I bring it back to 1. When I
but the way that you calculate the standard deviation, does it change when you pad with zeros?
Is it worth writing in? What's his name?
Yes.
Okay.
Yes.
I think that's
yes.
I rescaled my object.
And so this is where SNR is ill-defined.
Yes,
because
absolutely.
it depends on the size of your image. And so the signal-to-noise ratios that you are using there, I think, are unrealistic for compared to real data.
Right, but if you look at what typical images look like, it would be fair to say that the images do have some kind of look like that have an SNR of 1 over 40. As in, the objects are practically not visible. In fact, in a lot of the images that I've been seeing here, you have something more like an SNR in this definition of 1 over 10. I understand that SNR is ill-defined in this sense, and it's just a metric that we're trying to understand if we if we could compute what the power spectrum of the noise was, and if you could isolate all of these things, and in this ideal environment, what are the thresholds? And that is our goal in this setup. So I'm not trying to define the theory of what I said.
Conversation to the coffee break.
Yes. Yes. So let me just mention what the speedups are of these various algorithms. So we get a clean factor of 8 over what Nico was doing, just because we are searching 8 times as few rotations. But the big factor is strategies S3 to S6 more or less had the same recovery rate as strategy 7 when whatever we've defined SNR is to be a factor of 1 over 10, but the speed up that you get from there is another factor of 10 from that. So if you do some sort of frequency marching, you can easily get a factor of 10 over doing the full fine search in these setups. And the coarser you can go, you're obviously going to get those factors for free. So this is not even considering any translational filtering that we have done, because even for S3 and S4 as compared to strategy 7, we have another factor of 10 that we get for free. Just because we started off at a coarser grid and the time was dominant, we got another factor of 8 just from that, and then our local searches were very little time, and that is why I only chose like 250 or 1000. I didn't see much improvement, but at that point, it was more, when I looked at the image at that point, it was all noise. In terms of all of the cross correlations were like Gaussian noise, so there was no signal that could have been recovered.
And if you just look at the strength of the signal, essentially what you're talking about, the strength of the signal from the search model normalized by the noise, by the total image at any given band. Does this tell you what sampling you need to use? I mean, in the case of this particle, maybe you need to use kind of alpha Nyquist, right? But other times you may not.
Right.
And so, can you do a pre-analysis of those power spectra?
That's the goal, to see plots of power spectra of molecules versus these plots and how they behave with respect to different sampling rates in both rotation and translation space. Yeah. And essentially build a picture and then bootstrap to more complicated models where you have a collection of proteins sitting together. Right. So here are some things that are on our wish list currently. Faster template generation using non-uniform FFTs. So instead of doing interpolations, we can just take a spherical grid and use some sort of Fourier transform and squeeze out a factor of cube root of n number of rotations in this setup. Then optimizing parameters for our local searches. So figuring out what the right depth in our local searches to go to, and what kind of grid do we put down around each local point or each coarse point, and do our research. One free factor that's sitting there is just exploiting the symmetries of the proteins, right? The apoferritin molecule has a 48 degree symmetry, so I could have just reduced my search space by a factor of 48 for free.
Yeah, but that's not a general.
Yes. So when we go to the final setup of doing detection of simultaneous collection of proteins at the same time, the big goal is to cluster the proteins that look alike at certain scales and have certain symmetries. Use the reduced search space based on what symmetry group the collection of proteins belong to, and then when you go to the higher scales, or when you go back to the individual proteins, you still exploit those symmetries. So in the big picture, that's going to be important to use it wherever we can. As we said, use better maximum likelihood estimators, where we assume that the noise is not necessarily Gaussian and it's coming from more typical image, where we can estimate the power spectrum of the noise, or just use the power spectrum of the image as a proxy for the power spectrum of the noise, and build it into the model and understand the performance of different proteins and this algorithm in crowded protein environments as to how much accuracy do we lose if the noise was not Gaussian, and
So the crowded protein environment, should you start with it? Because if you find out that it doesn't perform once you have more than
Yeah,
a puffer
right,
in
that's
your
right,
sample,
yeah.
Yes,
then
that's the
you will
next
not
test
have-
actually, just to use a collection
Yeah.
of proteins and
Because
Gaussian
then you don't
resonance.
have to worry about optimizing
Everything.
anything. because
Exactly.
Nobody will use it. So.
Exactly. So
That's.
this is the next step for us.
Yeah.
Yeah.
Can you remind us what the bottom line of Nico's previous analysis was? How small of a protein can
150
you
kilodaltons in vitreous ice and 300 in. Sorry.
150 kilodaltons, and how thick is the ice?
I think it was 200 nanometers thick, if I remember correctly.
200 nanometers. Okay.
And this is in projection, right?
Yeah, it was a single projection.
Yeah, so
another
you're
thing
not
that
trying to do it from tomgram, which should be much better.
yes,
right?
exactly. So that's another thing we want to
Or
build
from
in.
the tomgram.
Yeah.
If we have alignment information, we can improve our signal to noise ratio by using the whole tilt series rather than just using a.
And basically, the thrust of your work is, can you do it faster so
Yes.
you can do it practically?
Right.
And
Right.
more. So it looks like you're hoping for a factor of 10
Yes,
faster.
at
Where
least.
does that put us in terms of feasibility? What if you did achieve a factor of 10 better?
Right. So
Would you be able-
it takes 20 minutes on a 20-core machine to do the finest search that we did, and it takes 3 minutes to do it on order a minute to do it for the core search. So on a simple 20-core machine for image
I thought you said Nico's was 100 CPU hours. or
100
something.
CPU hours. So if you divide that by 20, that comes down to 5 hours. You get another factor of 8 because I'm doing our finest strategy was coarser in rotation space by a factor of 8.
You know that the S7 was a speed up already. It
By a
was not
factor
at
of
1,
8.
it was already at 8.
Yeah.
Compared to Nico's.
Right, but S7 fails, with the lowest signal to noise, right?
No, S7 always
S7
succeeds.
is the finest.
Oh, okay.
Always
Sorry.
succeeds, yeah.
So just doing
and
the
that was
baseline is
already a
always fine.
factor of 8.
Yes.
Of course. Okay.
Yes, and
yeah, thanks.
and
Sorry.
and what's going to
Appreciate
happen I believe in crowded protein environments is I'm going to get pushed into that
Yes,
regime, and there's
that's
going to be a
right.
fall off there.
Yeah,
And
exactly.
but if Nico could have recovered that regime, I think using a combination of S7 and a fine search, we should be able to get similar recovery rates and similar false positive rates. In fact, our false positive rates will be lower than Nico's because we are searching a smaller search space than he is, in some sense.
You're going to say something about like dealing with decoys, right? Potentially different complements. How are you going to treat that?
So that is where we just said we leave it to the person who's analyzing the data. We're just going to ship a list saying that these are the locations where we think the protein is.
But you'll have to do some analysis based on
Right.
decoys and based on similarity of the decoys
Yes.
to one another and things like that, right?
Yes, so
Yeah.
that's really next on the wish list, and just analyzing first in crowded protein environments and then having similar proteins right next to each other and seeing what kind of effects they have where
It
we
doesn't
have
matter
a
whether they're
clean
right next
model.
to each other.
Yeah.
So you've not done any real
But
data?
let's take a break.
Not yet.
Okay, I
Okay.
would encourage you to do real data because it's very good.
It takes at least half an hour to get through the bathroom. So let's take a break. But come back here at 11.
One question to ask.
So you just type it and then assume it's
Yeah,
fine.
yeah, there we go.
Shall I put it on the screen and then
Yeah, and I would especially like
that one, eh?
And thank you all too. I mean, this is good. We very much appreciate it. Everybody come to New York.
Yes. Yeah, I think it was a really helpful discussion. It was kind, but exactly.
I think so. Very good.
I think there's pizza out there for people who want to grab lunch. Do you have a better pizza?